Redshift. So if you have a single, wow, that was 30 seconds for, but that was about the same for me for the rest of, or for the Spark SQL. When using this Hive thrift server, which is its own project, it has nothing to do with Spark necessarily. Spark is using it because they didn't want to have to write that code, but it's doing the adapting. But it's one single master, so one physical JVM that has to accept connections from all of the clients. So if you have 10 Beeline users, I don't know why you would use Beeline, but if you have 10 Tableau people connected to this, I mean, it's one JVM listening on port 10,000. And so all of these people are coming in, so they're all competing, number one, with bandwidth in and out, right? But let's, forget about the multi-tenancy part. Let's just take one query that comes in. If you structure the query such that you return a lot of results, so you just do select star from this table, so it's gonna be everything. All that data has to physically stream through. So think of inside the the JVM, it's like creating temporary objects and doing all kinds of buffers and sending things across the network and on all kinds of low level, but just from a high level, sort of like the whole just like an intuition standpoint, it's just so much data that's traveling through this single JVM that there's no parallelism, right? It's just one. So if you can structure that query such that all of the heavy lifting happens behind the scenes, so that's exactly what's happening with this query. Is I'm saying back in Spark land, right? Back in Redshift land, I keep making that similarity because it's the exact same problem. Do this average, find all this stuff for me, and just return to me the top 10. So physically through the pipe, it's just 10. It's 10 elements coming back. Versus get me everything, and then within Tableau, I'm going to calculate the average and calculate and sort it and do all that. So it's basically, if you did it that way, you're pulling in all this data that you just end up throwing out, right? Because you're very quickly. But sometimes you don't even know what you're looking for, right? Which is why Tableau isn't necessarily the best for the ad hoc analytics when combined with Spark, because it's better to go in and actually, at the Spark command line, so that you're not dealing with that super master. It's the same thing with Redshift.
When I was working in aerospace, we used Splunk, which
Yeah.
because we didn't know what we were reading.
Yeah.
We just wanted all the data from the plane real time, just send it to us. Let's see what's happening.
Gotcha.
But we're a little more selective. We might be able to do something.
Oh no, did my buddy leave? Right there? Trainer? That's going to be a bad review. It's tough when you are training two other trainers, because everyone has something to say. But yeah, that was really good feedback that you gave. So, that was that. I want to get into a relatively deep concept here, real quick. These last words. If you guys go to your, if you ever get lost, just go back to the main, just put in your IP address, and we're going to go to Zeppelin. If anyone's wondering why I changed this from port 8080 to 3123, I was at a hotel doing a talk, and they had port, 8080 was just locked down. It was totally, and we couldn't figure out what was going on. And Zeppelin is the crux of all my, and I was curling it from the server, it was fine, everything. So I switched it to something developer standard. They must have had some tool running on it. Okay, let's talk about approximations. This is kind of a decent segue from Redshift. So Redshift, looks like those guys took off too. Redshift gives you the ability, when you do a select, to put in the word approximate. This has been life-changing for my data science and research scientist friends who don't know about this. So for example, if you're doing counts, you can switch over to this approximate mode. And what this is doing is, when data is being added into Redshift, right, there's a small little data structure, it's called hyperlog log. It's named that way because of some of the math behind it, where it's sort of keeping track in a it's keeping track of counts, but in an approximate manner, in a really, really tiny data structure relative to the absolute count, right? So if you switch over to this mode, and there's a maximum error bound with this particular data structure. It's like 0.81%. So the total, that count that you get back, at most, will be 0.81% wrong. Which is, for me, trying to get error counts after I do a deploy, this is perfect. Like, I don't give a shit if it's 10% off. I just want to know, relative to the 15 minutes before, tell me, is it high? Is it much higher than it was before? So 0.81. So let me show you how these work. So Spark, of course, supports this. If you search the Spark code base, one thing I want to point out. The Spark code base, by the way, got like way more complicated after Tungsten. Things before were Java objects and all fun and friendly and readable, and now it's just byte array and kinds of crazy stuff. But if you, let's do our T, in this T, we'll do partial. Okay, partial results. Do you guys know about BlinkDB? You ever heard of Blink? So Blink, people over here, Blink. People always ask, why is BlinkDB not gone anywhere? Where is BlinkDB? No one's touched it in 2 years. Who is this guy? So this guy works for Databricks. Let's see when's the last time it's been touched. February 5th of 2014. So everyone's like, this is the greatest project in the world, came out of Berkeley. Samir is awesome, I used to sit right nearby him, cool guy. BlinkDB is essentially rolled into Spark. It's just that no one really talks about it that way. So there's this concept, for example, it's called partial result. Think of, from like now on, if there's one thing to take away from this section anyway, is never think of like an absolute query. Like when you're selecting, like doing counts and things like that, always think in terms of error bounds. Yes, always provide either I want my answer within 5 seconds, or cap of 5% error, something like that. Because otherwise, you're always thinking absolute, and you probably normally, not unless you're at a bank and you're counting pennies and things like that, do you need the absolute? So you'll see throughout some of this code. We're not going to dive too deep into it, but the ability to do a query. I think partial results probably like 2. So there's this entire package called partial. And you'll see everything in here, bounded double, approximate evaluator, approximate action listener. So the approximate, like action listener, if you guys can remember back to patterns, things like that, this is a callback, so that when I get to a certain point, call back with these partial results. So query, I send out the query, and then the driver is going to be listening on these sort of updates, right? So partial results, I think here, where do I actually specify? Approximate evaluator would be in here. So Snappy, the compression, Snappy. I don't know much about it, but I'm sure, yeah. I mean, does it use hyperlog log and bounded results and things like that? Yeah. What's funny is I worked at IBM for a bit, and I would explain during meetings what things were being worked on with Spark, and these guys are like, man, we've been doing this shit for 30 years. I just work with the project. I don't know. But, things like a lot of these optimizations have been happening with Spark SQL, and thing about managing your own memory and bypassing GC and all that kind of stuff. Yeah, this is all well-known stuff. It's just taken so many iterations to get in Spark. So bounded double. So here's where you would think, double value with these error bars and this confidence. So you give it a low and a high. So where's these guys. But the API is really clear. It's like, get me the results, and you pass in time and error bounds. I think I'm too low level. If I do T, hyperlog log plus. Okay, so Spark uses hyperlog log plus, which is a modified version of hyperlog log. I believe it was created by Google. State of the art. That's how cool it is. It's state of the art. Dense version of hyperlog log plus plus aggregate function. Okay, so this is the actual. So there's a couple packages to keep an eye on. It's this aggregate package, which is kind of all of Spark SQL's aggregation methods, and then there's the partial stuff. I'm looking for sum evaluator. Sorry if I'm making you guys sick here much, but anyway, yeah. Oh, and so there's, actually I think it's on RDD directly. This is a perfect example for T, because if I just search for RDD, it's going to be like 8 million things. So T, RDD, Scala. I believe on here there's a bunch of approx methods. You'll see these. We could probably look at Java doc too, but I have to go the hard way. So here we go. I was looking in the wrong area. So you can have an RDD, and this is supported at the data frame level as well, but here we go, just go straight here. So by default, it's going to be 95% confidence is what you are bounding this at, and then a timer. So how many milliseconds am I willing to wait for this answer? And it's running an approximate job. Count evaluator, let's look at what's on Spark context. Do you guys care about this at all? Is this interesting in any way? Run a job. So this is, so the main method here, yes, every method or job that gets submitted, this run job is involved. There's like one talk by one Databricks guy like 3 years ago that actually highlighted this. And to me, it's actually the most interesting part of this. It's kind of the core of Spark. So there's now this run approximate job where you give it timeouts, you give it a specific evaluator. Which I think this was the count evaluator. And there should be callbacks. There's a call site right here, timeout, finished. Just take a look at count evaluator. So you pass the confidence. It's currently allowed shared code. Some comments about code cleanup. Okay, so there's where you start seeing some of the initial approximation capabilities of Spark. This is BlinkDB inspired. In fact, I saw this prototype, one of the notebook vendors that may or may not be Databricks, had this one view I saw that had bounded error. So like you would run a query within the notebook, and you would see, like, as time would go by, that like error bars would kind of go closer and closer and closer. And then you could basically stop, like, whenever you were comfortable with a particular error bound. So yeah, from now on, think of queries, don't think of the absolute, think of error bounded or time bounded. Okay. So I showed you guys a little bit of hyperlog log. I want to point out another one that's in this. There's count min sketch. This package sketch kind of showed up recently. Let's see, when was the first contribution? Probably wasn't too long ago. Yeah, the beginning of the year. We're going to talk about count min sketch. So I showed you guys hyperlog log. Count min sketch is similar in the way that it works. It's an approximation. This is all for counting, right? Like all these things, aggregations, all these like analytic workloads. We're trying to count shit, right? So counting is very important. There's one more. Let me see what else is it. And then bloom filters. So my guess, and I seem to remember this actually, I could probably look at the JIRA, but my guess is Spark used to depend on the Twitter, or like Algebird project, which I mentioned. Someone asked about that at like one of the breaks. What is Twitter Algebird? What word are you even saying? Twitter Algebird. The examples I'm going to show you are actually using Twitter Algebird. I believe, because these are the exact three core like algorithms that are heavily used within counting and like the analytics space here. So bloom filter is very important. We're going to talk about these in a sec. Count min sketch, very important, and hyperlog log somewhere else. Twitter's up, and so I think they used to depend on this particular jar. And then throughout the last couple releases, they've been shedding like dependencies and like essentially rewriting just the things that they need from these projects. Part of the reason is when you go to write a Spark app, you guys have probably experienced this, and you also use Twitter Algebird, or you also use Guava, or you use Protobuf, and Spark is using Protobuf, but like a version from like 5 years ago. Yeah, what do you do, right? So you have to shade. You guys have probably heard about that, right? So in Spark 2.0, as much as as Spark could, they shaded all of their dependencies. So shading is where you prefix and put this sort of goofy gobbledygook namespace before the project that you're using, like the package name of the project that you're using. So for like protobuf, it would be com.google.protobuf. When you're done shading, all of the code sees that as like gobbledygook.com.google.protobuf. And that like gobbledygook is generated. There's like this like Maven plugin that'll do it. Like when you go to build your code in Maven, there's a plugin within was it SBT? Yeah, it also has it. It's not just rewriting the library that you're using, like the specific protobuf library. It's actually rewriting your application code that's using. So the only time that this breaks down is if you're using some kind of like reflection, where the name of that fully qualified package name has to be rewritten as well. And these plugins aren't very good about looking at a string and seeing that you're trying to do reflection and pull in a particular library. So just keep that in mind. But for the most part, you shouldn't have that issue like you did in Spark 1.6 and before, because Spark has done their own shading and rewritten all of their own code. So like you would never see that like gobbledygook, not until there's a stack trace. Then you'll see gobbledygook and be like, oh, where's that come from? And it's from the Maven plugin that first compiled the code, made sure it was cool, and then it went through, was trying to link everything, and had to rewrite and all that stuff. So yeah, so I'm sure that's probably one of the reasons why they pulled out Twitter Algebird as a full dependency. Okay, so are we ready for this? go to very top approximations 01. Kind of click around the code, but if you could just kind of pay attention for a few seconds here. Okay, the use case here, just to give you guys context. So why would I use hyperlog? This is specifically for count distinct. So there's count distinct, right? What we're trying to do, so this particular use case, I'm trying to figure out the number of distinct users who have viewed a movie in the past hour. This is pretty useful. This is used by Twitter, of course. How many, retweets for this particular story, for this particular link, how many followers, things like that. So, yes, hyperlog, the math behind it, which is pretty crazy, is such that so these items come in, so movies come in. I've chosen Top Gun, so this would be the movie ID for Top Gun. Let's say like 1005 or whatever. So, So this is the hyperlog data structure for Top Gun, and as users come in, right, that have user IDs, right, those user IDs get hashed in such a way that they're uniformly distributed. So this is the most critical property to this particular data structure. And so, so like I said, as data is coming into Redshift, it's constantly putting it inside of this data structure. Now, on the get side of things, right, like when you go to retrieve the counts, so I want to know how many distinct users for Top Gun. You can just look at one small little section that's right up front, and then you can sort of interpolate the rest of the count. So of course, we're only dealing with 16 slots here, but so by convention, you would typically look at just the beginning of this data structure, knowing that things have been uniformly distributed across here. And the more slots you give, so let's say hour 2 comes, this is like approaching peak time, the more slots that you give, right, the higher accuracy or the less error there would be between the actual counts and the estimated count, right? Because there's chance for less collisions and things like that to happen here. So so Top Gun, hour 2. What's cool too about this data structure is that you can actually collapse hours, right? Collapse times that are on different slot sizes, right? So these are like hash buckets. So you can actually combine across these different scales. Now you have hour 1 plus 2 and still get an approximation. You lose a little bit of accuracy, precision, I always screw that up. But you have, it's still better than having to do this entire full scan data count. So now let me show you one important property of these things besides the uniform distribution. So one slight detail here is that there aren't that many hash algorithms that give you uniform distribution. These aren't just coming out of our ass. So what actually happens behind the scenes is portions, there's multiple, so the same hash function is being applied to different sections and things like that. So it's doing some tricks to sort of work around the fact that there aren't that many of these. Because, as we'll see with count min sketch and Bloom filters, they rely on multiple hash functions, both in and out. So in meaning when I'm adding to this data structure and then out when I'm retrieving. So let's see. And then the other important property here is the size of this data structure. So here's just a regular, let's say I'm just maintaining counts, and let's say I want to maintain 100,000 counts. So I'm just creating a regular Java Scala collection here list of 100,000 numbers. I found this utility, size estimator. Getting a size of an object within a JVM is one of the hardest things ever, which sounds totally ridiculous, right? But if you've ever tried to do it, there's all these tricks you can do. You can turn on some weird Java agent when you start it up, and it keeps track of everything and slows down all your business. Or this guy actually, so he's actually like my twin. in like India. Yeah, he runs like a meetup, and he's always diving into code and everything. He actually found this portion of code that he repackaged as his own within the Spark code base, where it's sort of estimating the size, like without having to turn on those Java agents and such. And what Spark was using this particular utility for is to figure out when to spill the disk. Right? So picture mappers, reducers, the reducers pulling, grabbing all the data. Buffers are really growing and growing on the reducer side. Physically, the JVM holding this data. At some point, that JVM has to trigger a spill to disk. And it's a really hard thing to do, right? And so, so this utility kind of has all these different if statements, and if this is followed by that and stuff, just sort of trying to figure out how the JVM would typically do this. So this isn't like an exact count, but this is actually more accurate than a lot of other things I was trying to do. And so side note to the other side note about this utility, now that Spark has gone byte arrays with Project Tungsten, right? So everything's stored as like just a big ass byte array, and they're like recycling portions of the byte array as new data comes in and counts are being added and things like that. So this code becomes less important because now you could just call .size on the byte array and get the exact size of your data, right? So, this code still lives there in case you like totally disable Tungsten, which I still see a lot of people doing. So this is 100,000. I'm doing size estimator. Was it 4 megs? Is that 1,000 there? Yep. Yeah. So this is 4 megs just to maintain 100 elements. I mean, I haven't even really put any numbers in here except just the size of the list. Right? Yeah, because again, we're trying to maintain counts. So like this would be like 100,000 like items coming in or like something like that. Okay, so, or we can use hyperlog. This value is the number of bits. So bits directly affects this, right? The number of slots, right? The number of hash slots. So with this, and 14 also directly relates to the error. So 14 bits gives you 0.81% error. If you increase the number of bits, you would lower the error. This is kind of a good point. Yeah, this is what like Redis uses for their hyperlog support. 14 is kind of a magic number here. So now look at this size. So I put the same 100,000, that same list in here, and boom, 16K. It's crazy, versus almost 5 megs. So now picture, we're gonna get this weird accent. Picture, you're trying to do this all in like memory, right? Like you have these huge, like Twitter is just running clusters and clusters, and instead of, for 100,000 people, which is nothing for Twitter, takes like 5 megs of JVM heap. I mean, this is huge, right? And so just to maintain counts for their 50 million users or whatever they have now would take, just on paper, would take like so much RAM. So if you can really decrease that by down to 16K, this is huge. I can still maintain with a good amount of error. Okay. So let's go to count min sketch. So hyperlog was count distinct. Count min sketch is count. So it's like top K kind of thing, right? So this one's a little crazy to describe, but if you just kind of bear with me. So the use case here is I'm trying to find top K movies based on the total number of views. So I can zoom in. So every time I zoom in, like, this thing takes over. So we can just get. Come on. Grab the image. Okay, so what do we got here? Every movie, so each view that comes in. Okay, so each of these is, Top Gun has its own count min sketch data structure, A Few Good Men has its own, and Taps has its own. Has anyone seen Taps? Usually the older people. It's like Tom Cruise's, I think, like first or second movie. People keep disputing what was his first movie. I don't know. It was the first movie I saw with him. But they take over like a military school, and
Oh, I remember.
it's like Timothy Hutton's in it, and Sean Penn, and all of that. It's a great movie. Yeah, Tom Cruise dies at the end. Just gonna ruin it for you. All right, so each time, so picture, I'm taking Top Gun, I'm taking the movie ID, which, right, let's say this is 1005, I'm hashing it 3 different times. So this is what I was saying before, is that these algorithms want to hash things multiple times. And yeah, I'll explain why in a second. So we pick 3 hash functions. I don't know the details on how these functions are chosen. I typically just use Twitter's algebra, and they generate them out of their ass, out of the bird's ass, I guess. So if you hash it 3 times, take the binary version of that. Think of it like a grid. Think of it so that first one is 0010. So I've made this slightly complex, not on purpose. It was just the way that the diagrams were. So let's say Top Gun comes in twice really, really fast. And now I'm basically going to add 1 for each cell that I get to. So that first row is the first hash function, is the output of that first hash function. Second row, the output of the second one. So yeah, if you notice, there's 2's in there now. It's because that first one, that was the column that gets. And so yeah, I realized later that there's a slight. It seems like these can be, or right, that these have to be independent, but like you can actually have 1s in like multiple columns. It's just sort of the way that the way that I chose this, just to make it a little bit more clear. So that first row gets populated. Now the second movie comes in, Few Good Men. There's a collision, right, like so to speak, where the first hash function just happens to output the same as Top Gun, right? So we now add 1 to that slot, becomes a 3, right? So there's overlap, there's a collision there. But the second and third ones for Few Good Men actually hashes to these other like empty slots, so that's cool. Taps comes in, same thing, except now we have overlap with Few Good Men. Now on the get side, right, so this goes on and on and on. On the get side, I'm gonna, for the movie I'm trying to find, so this would be Top Gun, I'm saying, right, so hash with the same 3 hash functions. That's absolutely important. If it's different hash functions, this doesn't hold up well. Go to all 3 of those spots and find me the lowest value, which is why it's called count min sketch. The sort of intuition here is that you can always have collisions, right? So you can always overestimate, but you can never, if you grab the minimum, that is, like, yeah. So that would always be more accurate than something higher. Yeah, because you can always overestimate, but you can never underestimate. So, what was the other thing I was going to say? Oh yeah, and the more slots that you have, so here we only have 4 slots, the less collisions could happen, right? So this is where the size of the data structure, like you can increase the size of that data structure to sort of reduce the amounts of possible collisions, or you can shorten it up depending on your actual memory needs, and things like that. Okay? Does that make sense? You can always overestimate, but you can never underestimate. So always go for the minimum. Yeah, that took me like 2 years to understand. So, all right, and then Bloom filters, which are probably the easiest to grok, are very, very similar to count min sketch. So again, data's coming in, 3 different hashes, ends up in these 3 different slots. The main difference here is we're dealing with a bit vector, which can only have 1 or 0, right? So it's not actually maintaining counts. The use case here, just to be clear and point that out, is I want to know if this particular element is in this set. So the use case would be, of all the movies that Chris has seen, is this movie in there? And this could be if you very quickly want to filter out movies that you've already, that are being recommended that the person's already seen, or do some other kind of matching up. So here, this is the same thing where you can overestimate, right? So on the get side, you would apply those same 3 hashes, and you would look at all 3 slots and always go for the minimum. So the minimum here, so we're going to now flip over to true and false. The minimum between 0 and 1 is false. So if there is any 0 at all, that means I'm definitely not in this set. So now this guy, it's all 1s. The problem is that there was a collision over here, so it's not guaranteed that that element is actually in the set. So you can get, I guess, was it false positives, or, yeah, I screwed that up, but you can think something is in there, but you're not guaranteed. So that's the overestimation. 1 is you're overestimating positive. What you would do in that case is you would then have to scan the entire data or the file that you're looking at. So think of, so this is used heavily in like Cassandra and like various other places where if you're trying to scan a file system, so let's say data's coming in, streaming data's coming in, boom, 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 you're sort of building up files and like data on those files. If each time that you create a file, you can create this tiny little Bloom filter that when hashed, tells you if something is in that big file or not in the big file. This is really useful because if you're scanning along the file system trying to find something, you just have to crack open that first bit vector, run the hashes, which is really fast, boom, 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 and get back 0 or 1. If it's a 1, that means it might be in that file. Then you go scan the file. But there's going to be a lot more, typically probably like a lot more, it's not in this file, not in this file, not in this file. So same with like distributed systems, if you're sort of poking around, trying to search your like cluster of nodes, you can, so if there's Bloom filters that are being maintained, so the key to these data structures is that you don't update anything. Because the second that you update or delete, then all these properties kind of go away, right? So things can like only be like added. Otherwise, you don't know if there was at some point a collision or what was going on there. So surprisingly, it has a lot of use cases. Probably wouldn't really get to that level, but definitely use this approximate thing. Just one thing to learn out of here. The difference. My one research scientist friend, she's been using Redshift for a couple of years, whatever now. And I just happened to mention it because I was studying up on Hyperlogler, and I mean her queries were down in the seconds versus hours range. So pretty cool. So here's an example. Here's 100,000 converted to a list. We use our buddy's size estimator. What's the size of this thing? 176. So yeah, these are bit vectors. Cool. Here's locality sensitive hashing again. Just keep that in mind. It's another approximation. It's all part of Twitter algebra. I have the code examples here, breaking up into 50 buckets or 10 buckets or whatever, and kind of zipping through it. Approximating. I showed this Thursday. Some people have probably seen it. There's this fun little graph recommendation, like besides the obvious, PageRank, degrees of separation, all that stuff. There's this cool recommendation demo that I saw like a while ago and finally decided to like implement it with Spark. If you're given, I call it sort of like couples recommendations or compromises when like you don't want to cause a problem in your relationship. So if it's a Friday night, you're sitting down, you want to watch Toy Story, your partner wants to watch Sudden Death, how do you decide between these, right? So like show me some possible compromise recommendations. What's funny is actually, I think it's Comcast Labs or the Xfinity Labs, like so you can install this type of app. If you're brave enough to install anything, A, by Comcast, and B, that's marked Labs. But you can actually have I think it's up to 4 people, and you can select all, 4 of you and 3 other friends can select what you're interested in watching. and it'll make recommendations and show kind of similar movies to all 4 of those. So this is sort of a generalized version of that. It's 2. Here's me trying to do D3 inside of a Zeppelin. Right there, closest I got. Let's see, personalized page rank. So the intuition here is we're going to pre-process all the movies. So this is a very expensive task, right? You're basically finding similarity between all the movies in this universe. So this universe, I think, only has 10 movies. So this one's pretty fast. And then each node in this graph is the movie ID. Every edge is the similarity weight. And so what you're trying to do is, given a starting node, find me the heaviest weight. Right? So it's like, Dijkstra, but kind of the heavy Dijkstra, not the skinny Dijkstra. So based on this, we kind of crawl through, and what do we got? We got, starting with Toy Story, we have Jumanji, Jonathan Taylor Thomas, and Tom and Huck, GoldenEye, Heat, and finally Seven Death. So somewhere in there is a relationship-saving movie. Probably Heat. Would you guys go with? Jumanji. Where is this kid, by the way, these days? My sister loves him. Okay, so the similarity, the way that I've defined similarity here, is specifically based on the genre. So this comes out of the the movie lens data set, the classic one. Every movie has a set number of tags that someone sat down and typed in. And we're defining similarity using Jacquard similarity, which is a way to compare sets. So if I have this set and I have this set, give me some number. And it's the intersection divided by the union of the 2 sets. So, and then, once all that's pre-processed, then find the heaviest weight. And it'll show me this sort of path through. So this was inspired, there's this really cool project called Boil the Frog. Came out of this company, was bought by Spotify. It's called Echo Nest. You can do Weezer to Lady Gaga. It kind of shows you this path. You can kind of reason through. You get to some weird ones here, but Britney Spears is on there. What was the one I was trying to do the other day? It was like Metallica. Kansas. It's pretty funny. Genesis. And so picture, probably Genesis would be in the middle of a lot of these. Carrie Underwood in Hunger Games. She sang on the soundtrack. I've seen this demo generalized even further into books and records, music, things like that. It's kind of cool. Speaking of recommendations and that kind of thing, let me show you guys this. So there's this really, this book is probably one of the best books on machine learning, not just because Nick's my friend. And I brought him on to the Spark Tech Center, the IBM Spark Tech Center. That was one of those, hey man, come on board, and then hey man, we'll see you later, have fun. He is a PMC Spark Twitter dude out of South Africa. Wrote that book. There's a lot of really good demos in there. There's this other blog post that if you haven't seen it, it's probably the funniest thing. This is one of your favorite things, Andy, isn't it? Tinderbox. This has powered me the last 2 years of my life. Oh, he doesn't even have Tinderbox.com. So this guy is from Vancouver, Canada. I have to specify that. He's since created this dating site called Birdie AI. The context here is he reverse engineered Tinder, the dating site, when you swipe, it presented pictures and then boom, swipe. And yeah, so there were two big features out of this. One was, so after he swiped, I think about 150, 160 times, it would train this like Tinderbox app into what you liked, what type of facial features and things like that, right? So of course the faces all have to be aligned properly, and yeah, like there's a lot of questionable things in this blog post, but the point of it here is pretty good, and yeah, going ahead and like built this in Spark. So yes, over time you can actually have Tinderbox swipe for you essentially. So it's reverse engineered Tinder's API. It's getting the pictures. It's already learned your taste because after a certain number of pictures, you can use eigenfaces. You can sort of decompose the picture into simpler feature set or like principal components, and then from there, then you can quickly swipe left or swipe right. So let's see, there's some code. It's not Spark code. I actually contacted him right after. I'm like, hey man, why don't you use Spark? The second thing, and I'm going to show you guys the example here. Using Stanford Core NLP, which is an NLP library, to do this sort of conversation, this like automated conversation thing, where you would softball out sort of a, hey, yeah, my name is Chris, how was your weekend, whatever. And then based on their reply, right, like sentiment analysis, take their reply, either go fuck yourself kind of thing, or hey, yeah, you're cute, let's go hang out. So yeah, after a certain time, like this would actually surface up both people that were swiped because they fit your sort of average or principal componented face, and then also people that have like positively accepted your sort of generic starting move there. So yeah, this is the dashboard he created. Yeah, he said he was saving so much time in swiping, he was able to create a dashboard. Yeah, like this guy is awesome. And yeah, here's all the code. I think he even says in here, like, I cannot possibly keep up with everyone trying to commit to this. As soon as you turn on this bot, it will start messaging all of your contacts. Yeah, I think he puts in here, he's like no longer supporting this. Anyway, so this is applying AI to dating. So this book actually has a similar example. I've chosen this pretty cool data set. It's called Labeled Faces in the Wild. So this is about, I think it's 1,600 people, I think like 30,000 or 13,000 or something images. And they've all been pre-aligned, so they're all square this way and not, tilted and things like that, which is not an easy thing to do, of course. So I take that data set, I run PCA on it, it just gets the good stuff here. The top 8 principal components for this data set. So what I've done is I've actually flattened out the 50 by 50 pictures, right, those images into 2,500 wide vectors. Each element within the vector is the gray scale value. And then I've gone ahead and done PCA with Spark. I give it 8 just because it fit on the screen good at some conference I was doing or whatever. So I probably could go bigger here. You could kind of see some of the features coming out. Oh, and so then once I've defined, I've calculated those 8 principal components, I then reconstruct them from the 2,500 wide into 50 by 50. So this is what visually ends up being the top 8 eigenfaces. As PCA, these eigenvectors describing, it's sort of pulling out the most descriptive pixels and things like that of this full data set. So give me the top vectors that describe this data set. One thing about PCA that please keep in mind is it's very difficult to, and this is a classic problem with PCA, it's pretty well known, but you can't really go from these 8 these 8 principal components to actual human interpretable features. yes, only visually could you be like, oh, okay, I kind of see smile lines right there, or this, these eyes are this far apart, and hairstyle is kind of like that. But yeah, no matter what you're doing, like people want to go from these PCA things to the human features, just from a grokking standpoint. But yeah, that's not how PCA works. So let's apply this and have some fun. Let's go back to Tom Cruise for a second, TC. So now that I can represent all, 13,000 images as just 8, I'm now projecting these 2,500 wide vectors for each picture, 50 by 50, flattened out. I projected them down into just 8 dimensions, 8 features, I guess you'd say. So now that I can do that, I can do this quickly. I can compare and do an all pairs comparison. If I pass in one picture of Tom Cruise, find me the top 5 images based in this PCA space, this new 8-dimensional space, not the 2,500 dimensional space, which would be computationally difficult. So yeah, show me the top 5. So let's see what we got here. We got Boleen. She's a real fun-looking thing. Candace Sutton, I don't really know her, but cracks me up. It's another female. Gerard Schroeder, Yuri, first astronaut to get married in space to someone on Earth. Russian. Yeah, these 2 Russian guys were at the Duke Summit. They were sitting right in the front row. They were cracking up. And Cheryl James. So top. So now this is based on an 8. I've projected these down into 8 dimensions. So this is probably want to go a little higher if you're going to do anything useful, but that's kind of cool. Something to keep in the back of your head if you're going to do any image stuff. One thing, if you do have images that are skewed this way and that way, and you basically can't do this, right? You have to use rather convolutional nets. And actually, this data set, the one I chose, there's different versions of it. So they've already done the sort of convolutions around. So they've used deep learning to even choose these rather specific images. So yeah, there's a lot of pre-processing involved there behind the scenes. Okay, one thing, someone asked us earlier about Spark SQL. Right, like when I say Hive, yes, I mean Spark SQL's Hive. Right? Yeah, so nothing we've discussed today will involve Hive itself. There's the Hive metastore. So one thing I want to show, if you're looking for the best performance, so here's all the options. You have CSV that's unpartitioned. We're joining it with this other CSV, Parquet, unpartitioned, partition, things like that. So I've gone through, I have Avro in here, I have Orc, I've got Cassandra. At one point, so some of these data stores, like Cassandra, like Elasticsearch, support partitioning, support data locality, right? Like some of these like data frame plugins are super advanced. Yeah, so just in case you're taking a look at SQL 01. So I'm basically doing joins on like everything with everything in all different shapes and sizes here. So of course, and then here's all the physical plans and everything. I'll talk about this in a sec, how to read these, but the winner, so I like to give away the winners here. It's typically, like almost always, Parquet partitioned with Parquet partitioned, right? In terms of speed. So this is the exact same data set, it's just that this has been partitioned by, I think I'm doing a join on the, I can't remember, but yeah, right, like whatever it is the partitioned column that I've chosen. So you want to partition things, you first want to look at your use cases and figure out how are you actually querying the data, choose the partitions that. Orc partitions is pretty fast, of course, Avro is pretty fast. Cassandra, I thought I found a bug, it turned out I didn't have some configuration turned on or I was doing something weird. So the way to read these, not sure, if you guys have probably done this before, but if you have this data frame, you can actually call explain. And if you pass true, it dumps out all 4 stages. So if you don't pass true, it's just going to return the physical, which is probably like the only one that you really need to know. So this is, physically what has Spark decided to do here. If you kind of take a look though, you can see the thinking here. Here's the parse logical. So this is just, what am I doing? I'm joining the rating CSV, which is like user ID. So this is this like dating data set that I just got a hold of. It's like an anonymous data set. We have user IDs, you have a rating, and you have their gender in another file called genders. So here I'm just joining all that data together. And the true, as you kind of see, here it's just figuring out what are all the nodes in the AST. Boom, CSV relation. Oh yeah, the way to read these, by the way, is bottom up, which took me like 3 years to realize. Because if you go the other way, you're like, well, I kind of see it, but it doesn't make any sense. So start with the bottom. Typically, the bottom is going to be the file system or the Kafka topic that you're looking for, or the particular offsets, things like that. So here's the physical plan. The very bottom, we're scanning this file. This is the ratings file. We're filtering. So each step is one pass through the entire data set. That's kind of how you can think of it, right? So here it's pulling in all the data. Here we're now going back through and passing through. So fortunately, Spark SQL, yeah, so this is what I was saying about the IBM guys, like, man, we've been doing this forever. Fortunately, Spark SQL can combine these filters and say, well, instead of making 2 separate passes, which probably my logical, yeah, so this logical, the query I'm filtering and saying, get me only people between 4 and 6 that have been rated 4 and 6. Find like the not so good looking people in this data set. So here it's able to collapse these filters into one pass and just can do both sides of that filter. And then this tungsten stuff all of a sudden pops in and you're like, I don't know what the hell's going on. But just kind of think of this as here's where it converts it into tungsten by the way land. Just keep your fingers crossed. What you want to make sure doesn't happen is, yeah, right? Like you want these to be as collapsed as possible, of course. Let me show you one that's really bad. Which one is this here? This is the longest variable name ever. It's like how I remember. I should just document it. I should just put a comment. I don't know why it's going to be gigantic. Unpartitioned JSON with unpartitioned JSON. So this is going to be horrible. Yeah. So help Spark help you by partitioning. And one thing to note, are you guys familiar with this broadcast hash join business? So I think in the Hadoop world, it's like a map side join, right? We have a small table being projected out, and it's being projected out to each node, and then each node can then join locally instead of doing this gigantic shuffle. And so if there's a huge disconnect between large table and small table that you're joining, like a state table or a country table or something like that, you want to make sure when you inspect the physical plan, and yeah, now there's a way to see it, I think through the Spark UI, you can actually see broadcast hash join instead of doing it this way, but you pretty much want this all the time. There's one configuration, and actually someone brought this up the other night on Thursday. It was one of the Zillow guys was talking about configuring this. The way Spark before 2.0, so 1.6 and before, so the way Spark would figure out when to use broadcast hash join, when to decide that small versus large table, there was one value in the configuration that really nobody knew about, and not unless you've been burned by this a couple times, where it's the maximum limit to how big the small table can be. So I think by default it was 10 megs. So if your state table or whatever smaller table that you were trying to join against was more than 10 megs, if it was 10.001, if it was 1 byte over, it's not going to participate in this broadcast hash, which is kind of ridiculous. Also, one thing that burned a lot of people this took me a while to actually figure out as well. On disk, if that file is 10 megs, it's not 10 megs in the JVM. It's 40 megs. So you might think, well, I've set this value at 10, and my Parquet file, it's 10 megs. Why isn't it? It's because by the time the JVM is loaded this into memory, you're now dealing with a 40 megabyte data set size, which is way beyond. So you start to get into this, well, let's just set it a little bit higher, and then the other team comes over, well, I want it to be a little bit higher, and then so unfortunately 2.0, and I hope this is enabled by default now, but this is more heuristic based. So this is actually, this was another thing too. The IBM guys would rip on, like, how is this not heuristic based? Where's the cost analysis and all that? Like a lot of this stuff now is being figured out dynamically. And what's cool too about the new broadcast hash join, it can actually figure out within a data set that you're operating on which keys are the hot keys, and then just broadcast those, right? Because why would you broadcast the entire data set if it's just a small offending set of keys? So actually, within stages, you'll see some part of the stage is using broadcast and some of it isn't, and that's okay. Yeah, hopefully that's okay. Did I show push downs? I don't think I showed. Actually, I think this is a push down. So essentially, certain data sources you can turn on push downs, pushing it down. And so Cassandra supports this. At the low level, Cassandra knows where all the values are that you're trying to find, all the keys are from the token array and things like that. So you can actually push down into Cassandra and say, just return me the keys, or the data I'm looking for. Don't, which sounds silly, sounds like that's how it should be. It should be for sure, but the sort of early versions of these plugins didn't do that, right? Because Spark didn't expose that as a way to filter. So Spark could do it. Spark could do it with Parquet. Spark could do it with certain data sources. But if you were writing your own custom, there was physically no API hook to let the source push down. And then furthermore, for about 2 or 3 releases, Spark would, I guess you could say Spark didn't trust your push down. So no matter what filters you did in your source, Spark would always do one full pass over and filter out just in case, right? That's been since lifted in the sense that it does it by default, but you can disable it as the plugin, as the data source plug or builder. So that directly came from the Cassandra guys. They were like, hey, now we've done all these optimizations, and yet we're still doing the full pass over the data set that gets returned to you. It's still a smaller data set because we've already filtered, but that means you not trust us. What's the problem here? So Parquet supports pushdowns, of course. Yes, everything is like Parquet within Spark. I mentioned the standard core NLP stuff. Let me show this real quick, and then maybe a couple break. So there's still coffee in there, right? I hope. Is it fresh? Okay, Stanford Core NLP. Spark ML has its own concept of pipelines. It's derived from scikit-learn's concept of pipelines, where there's transformers and estimators and evaluators and things like that. Spark was developed in a lab, came out, a lot of people started using Spark ML. They're like, wait a minute, as part of scikit-learn, I've always had these pipelines, and there's a lot more than just building the model, there's feature transformations and normalization and standardization, things like that. So instead of creating their own sort of concept, they just took the same terms from scikit-learn. So one really cool thing is that we finally got working is Stanford Core NLP, which is like this natural language processing library from Stanford. It's been developed for years and years. It's pretty much, as far as I know, people doing Java with NLP, they're pretty much using this library exclusively. So, so the ability to take Stanford Core NLP and then make it part of the ML pipeline, this is pretty huge, right? So this is just it's a feature transformer. So I'm passing in lyrics. Here I've done country music, and I'm going to calculate sentiment analysis so on these country songs. And it's taking each song that's been given, and it's transforming it. It's doing sentence splitting, which is tricky within country music, I've come to find out, and stop words and things like that are kind of funny. So what do we do here? So we make this part of a pipeline. So this is actually, this was developed by Databricks. It's kind of wonky to get working. It actually took me and the HomeAway guys a couple weeks to, back and forth trying to hack things together, but I finally got it. So it's going to tokenize, it's going to do sentence splitting, which is actually really hard, not just in country music, but anything. Parses it, does sentiment analysis, runs the transformer on the items given, which is each song is an item. And then, what do we do here? Songs. Oh, yeah, so this is the actual sentiment analysis. So what is it? So this is how long it took. 7.5 hours to do sentiment analysis on just 100 songs. So this was on our servers, the 8 cores and that kind of thing. So my guess is the Stanford Core NLP stuff probably, or at least sentiment analysis, probably isn't parallelizable, which I don't understand why it couldn't parallelize each of the songs. They don't really depend on each other, so I'm not quite sure what's going on there, but it shouldn't take 7.5 hours for that small data set. So if you're curious, these are the results. There's a lot of negative sentiment within country music. Surprise, surprise. It is unsupervised. Sorry? Well, it's using, it's just whatever, Unsupervised lexicon. Wow.
We end up using OpenNLP.
Yeah, so I know. So maybe it's the transfer of those jars, maybe, but it's a single node.
But even all that stuff that we see around it.
Yeah. I didn't think about that. All right, so let's step up the game here a little bit. You guys want to do? Oh, there's one more on the synonym. So here's Word2Vec. If anyone's used Word2Vec, the Word2Vec in Spark is pretty bare bones. You can only do synonyms. So I've done the same thing with country music, typed it in here, trying to find words similar to truck. What does it come up with here? Likes, heard, news, gave, heart. Kind of interesting. Love. NASCAR. I like that NASCAR is a synonym to love. And God. Burr, shame, proud, pick your God. I never really heard that in a country song. Okay, how about let's do like a 10-minute break, and then after we're all going to build a big Spark cluster. Is that cool? And then I'll show some TensorFlow stuff too as well. save the TensorFlow for last. So yeah, 15 minutes, which will end up being 20 minutes probably. 4 o'clock. Yeah, we'll go through that. Yeah.
My wife came in and told me. What is it? It's her schedule once her in November. I'm attending on a one-nighter
I have dinner or something. I have no particular plans other than the website because we meet Friday to see UNC professor.
Yeah.
And on Tuesday, on Friday.
Yes. When do you take off on Friday?
About 7 something.
Because those are all. So that's back and forth. Really?
What does he do? It's like it's some kind of flow. Is he? Which department?
Not within a just that.
Yeah.
This part. There's an example in there.
Oh, I see.
Yeah, because he said they don't actually do, they didn't respect. I think we have to look at the top. It's a 1.9.
E3 has
Or
our
1.9. Yeah, yeah.
So, kind of risky.
491 express.
Assessment combinations.
Yeah, forever.
Yeah, like some of the
The big carrier that gets from what he
issues with instrumental condition A, B, C, C. It's also possible that some state they have no those could be events. They could also have it's not the same. Might be see some doctors observation